If we had a single non-zero vector, its span was the set of all linear combinations of that vector, so any multiple of u. And if we trace out all the different multiples of u, what this forms is a line. Now, similarly, we talked about two vectors and their span, so any two vectors that you could combine in this way. We showed that this ended up forming a plane. But there was an important note. The vectors u and v had to be different enough. And I'm putting different here in quotes because I haven't really defined what that meant. And the important example here that I went through last time and that we're going to talk about again here is if, for example, I tell you that one of the vectors is twice the other one, then you can clearly see that v is a linear combination of u. It's the only combination you can form of one single vector. They're multiples. So when they're multiples like this, the span of u and v would simply be saying, let's form all of the different combinations that we can of these two vectors. But because we are just talking about a multiple of one of them, you could combine both of those constants out front, and you essentially just have one multiple there. So the span of those two vectors wasn't really different than the span of just one of them. It's still a line. If you have some vector a3 and it's 5 bunches of a1 and 6 bunches of a2, and let's say we know that a1 and a2 are not multiples, so they are different enough, then the same sort of discussion happens. If I want to talk about the span of a1, a2, and a3, I'm interested in what types of vectors I can form by making linear combinations. Because I have some special information here about a3, this expression becomes a little bit different. This expression is c1a1, and then I can combine things in this way, but I now get to substitute this in. And because of that, I can once again group together all the bits with the a1, and I can group together all the bits with the a2. And this is some constant and this is some constant. So I just get an alpha a1 and a beta a2. So what it's telling me is that those three vectors aren't really different. The span of the three of them isn't going to give me anything different than the span of just a1 and a2. And these two examples give me a clue as to what it means for us to be different. We're going to make an important definition. Linearly dependent vectors. If you've got a set of vectors, v1, v2, and we're going to assume they all have the same number of components, a set of vectors is linearly dependent if any one of them can be written as a linear combination of the others. In the previous examples, the set u and v is a linearly dependent set because v was twice u. Twice u is a linear combination. We are going to say that a1, a2, a3 is a linearly dependent set because a3 was 5 bunches of a1 and 6 bunches of a2. They are a linear combination. If a set is not linearly dependent, then we give it a different name, a linearly independent set. We would like to figure out if a set of vectors is linearly dependent or not. So how do we actually determine if a set is linearly dependent? And the definition is going to give us clues. From the definition, it says in order to be linearly dependent, one of them has to be a linear combination of the other ones. So back to our first example, if v was twice u, then if I reorganize this equation, I'll get that twice u minus v is equal to 0. So it's possible to add them up to get 0 in what I'm calling a non-trivial way. By contrast, it's always possible to make vectors add up to 0 in a trivial combination. Trivial is a word that kind of just says, duh, it's so easy, everybody should be able to see it. Well, this is the trivial combination. 0 bunches of u plus 0 bunches of v does always give me 0. This example here was a non-trivial because there were 2 of them and -1 of them. In the other example that I gave you earlier, A3 was 5 bunches of A1 and 6 bunches of A2. I can take them, 5A1 plus 6A2 minus A3 is 0. They can add up to the 0 vector in a non-trivial combination. To help us figure out whether or not a set is going to be a linearly dependent set, we're going to build off this result. We are going to let A1, A2, and A3 form the columns of a matrix. By definition, this is some matrix vector product where A has the columns A1, A2, and A3, and X holds the proper weights. And this is going to give me 0, 0, 0. We have a linearly dependent set by definition, and this gives us a non-trivial solution to this homogeneous equation, AX equals 0. And again, the matrix A has the vectors that we're interested in as its columns. We have a non-obvious, non-trivial way of getting a solution to a homogeneous equation. So this allows us to generalize. If you have a linearly dependent set, one of the vectors is a linear combination of the others. You will be able to rewrite this as a non-trivial combination that gets you a 0. So you'll have a C1, V1, all these other vectors down to Vn minus one bunch of Vj is going to give you 0. And so what that's going to do is produce a non-trivial solution to this AX equals 0, this homogeneous equation. You're going to have a matrix V1, V2 all the way down with the Vj, C1, Cn with the -1 equals 0. And so the point of the story is to determine if a set is linearly dependent. What we need to do is check for non-trivial solutions to AX equals 0. And we'll talk about that in the next video.